Hi guys, this is section 8.2, homework number 3. In this problem, we are given C is the circle relation on the set of real numbers. What does that mean? That means specifically it is defined here. So for every xy in real numbers, x and y belong to relation C if and only if x squared plus y squared is equal to 1. That means x and y, they are on this unit circle, right? So now we are going to check through all these three properties and determine whether which one is true for this relation. So the first one is let's determine whether C is reflexive or not. So now in order for us to say C is reflexive, we have to show the following. So I'm going to write this down. So we're going to say C is reflexive, if and only if, right? If and only if. Now we're going to copy down this one. So for every real number x, well, you really don't have to repeat for every x comma x in R because it's the same. So for every real number x, xcx, that means x belongs to this relation if and only if x squared plus y squared plus x squared equals 1. That's how we define the reflexive. Now let's check. Just imagine, try some numbers, right? If x, say I can name, suppose when x is equal to 0, then x, so 0 squared plus 0 squared, this is definitely not equal to 1. Okay, so therefore this actually is a counterexample. This shows that C is not reflexive. Is not reflexive. Okay. Well, certainly different people pick different counterexample. You can say when x is 1, so 1 square plus 1 square definitely not equal to 1 square. So this definitely shows that it's not reflexive. So but you cannot say when x is square root of 2 over 2 and then square root of 2 over 2 square plus square root of 2 over 2 square equals. Actually, it is equal to 1, right? But however, you cannot prove something is true using a specific example. Yeah, this is just a special case, shows that when x is square root of 2, this property is true. However, it is not true in general. So we disprove this using a counterexample. Okay, so I'm going to erase that because that should not serve as a proof. Now let's look at the second property, whether this C is symmetric. So, well, this is actually pretty easy to show. I would encourage you to pause the video and think about it yourself first. Now, if you resume your video, this is what we are going to show. So I actually know it is symmetric. So this is, if it is symmetric, so this will be true. C is symmetric if and only if. So for every x, y in R, right? If x, c, y, that means x, y is belongs to this relation, then y, c, x. Okay, so that's it. This is a if then statement. It's a conditional statement. So let's assume this is true. Okay, assume this is true. We want to show this is true. If you show that, that means C is symmetric. So now, because we are gonna assume, so if x c cy, that means xy belongs to the relationship, then this is true, right? So that means then x squared plus y squared is equal to 1, okay? Now, sometimes look at what you want to show. This is you really want to show. What does it take for y comma x belongs to the relation? If you look at this definition, so y comma x in this relation, that means y squared plus x squared equals 1. So that's what it takes. That's what it takes for you to conclude this one. So we already know this, okay? We already have that. So when this is true, definitely this is true because addition is commutative, right? So then y squared plus x squared is equal to 1. This implies, right? This implies according to how the relation is defined. So this guy certainly, this guy comma this guy is belongs to the relation. Belongs to the relation. So this implies y cx. Okay. So therefore C is symmetric. By the way, what I'm writing here is not my proof. It's just an interpretation. Before we claim it is symmetric, this is what we want to show. Okay, this is something that I want to show, just interpretation. Here's the proof. All right. Now let's take a look at the transitivity, the transitive, whether this relation is transitive. So now again, I'm gonna interpret like what it takes so that we can claim the relation is transitive. So here's what has to be true. So before you can claim, so C is transitive. If and only if for now transitive involves three elements. So three elements. So I'm gonna say X, Y, Z. Okay, in R. Okay, and for transitive, this is actually a conditional statement. If X, C, Y, that means X comma Y belongs to the relation, and Y, C, Z, that means Y comma Z also belongs to the relation, then we have to show, in order for us to claim the transitivity, then we have to show that X, C, Z, right? That means X comma Z belongs to the relation. So let's see if this is actually true, okay? So I'm gonna say, you play around with some numbers. I actually know this is not gonna be true. This is false by showing you a counter example. This is false. And here's the counter example, okay? Here's a counter example. And let's pick some nice numbers. So pick two numbers so that these two numbers are on the unit circle, like 0, 0, 1. So I'm gonna let x equals 0, y being 1, then and z is equal to 0 again. So you can see that x and y, x comma y belongs to the relation because x x squared plus y squared, which is 0 squared plus 1 squared, which is equal to 1, right? So this is because of that. And then y and z, they belong to the relation because y squared plus z squared, which is y is 1 and z is 0, also equal to 1. So you already see xy belongs to the x comma y belongs to the relation, y comma z belongs to the relation, and we just show that. Now however, now y, actually the transitivity, right? X squared plus z squared, which is 0 square plus 0 square. This is not equal to 1. That means x comma z is not in this relation, okay? Because if x comma z, this pair is in the relation, then x squared plus z squared has to be 1. So now you can see that this is not transitive. So therefore C is not transitive.